Hi everyone. There is one last result that I want to prove before we move on to actually constructing the real numbers. We're coming full circle because what we're going to prove here is that for every real x greater than 0 and every integer n greater than 0, there is one and only one positive real y such that y to the n equals x. In other words, every positive real has a root of every number, no matter whatever n is. So this number is written as the nth root of x, or x to the 1 over n. The reason this is so interesting is that we started by observing that the square root of 2 is not an element of the rationals, and that for a set such as the p's in the rationals where p squared is less than 2, there is no least upper bound to this set. So we defined a set that has a least upper bound property, which means that every set that's bounded from above has a least upper bound. And what we've been looking at is the implications of that. But what's really interesting is that we have not actually solved the problem, because we've said that this set has a least upper bound, but we haven't said what it is. We haven't said what is the square root of 2. So what this proof does is it demonstrates how we can find these roots or define these roots in the real numbers. So this is going to be fun. This is, I think, the most difficult thing that we will have done so far. It's quite involved and very interesting, and it also shows how we use the least upper bound property, and it shows why real analysis can get so difficult and detailed and hard to get the precise. Everything that you want to do can take like a lot of effort to get it done. So without further ado, so the first thing is just to prove that it's unique. Remember, the claim is that there's one and only one. So not only is there a root, but there's only one root. So first we're going to just show that it's unique. So that there's only one such y is clear, because if we had 2, then this implies that y1 raised to the n is less than y2 raised to the n, meaning that they cannot both equal x. If one of them equals x, then it's going to have to be smaller than the other one. So did that make sense? If we have 2 separate numbers that might be the root of x, then one of them is going to have to be less than the other one. And if that's true, then one of the powers is going to have to be less than the other one as well, so they can't possibly both be x. Okay, so if we can find an answer, it will be unique. So the existence. So we're trying to show that there is going to be a root of every positive real in the real numbers. So let's let E be the set of all real positive numbers t such that t to the n is less than x. So what we're going to show is that we're going to show that the least upper bound of E y equals sup E is in fact the nth root of x, then y to the n equals x, as desired. Okay, so we start with this set. We have to show that it's going to have a supremum, and that supremum will in fact be the nth root of x. So to do this, now it gets involved. So to show that if we're going to talk about the supremum of E, the first thing we have to do is show that in fact E has a supremum. And to show that E has a least upper bound, we need to show first that E is not empty, and two, that E is bounded. Above. Okay, these are the requirements. If a set is not empty and is bounded from above, then in the real numbers it will have a least upper bound. So first, we have to show that E is not empty. So that means we have to show at least one t to the n is less than x. So we're just going to try to find a t such that t raised to the n is less than x. So let's look at t equals x over 1 plus x. Then we can show that t to the n is less than or equal to t is less than x. So then t to the n will be less than x. Okay. Next page. Okay, so first we're going to show that 0 is less than or equal to t is less than or equal to t is less than 1. Now, that x is positive is given. So 1 plus x is greater than 0 as well. And that means, remember, that t equals x over 1 plus x. So if 1 plus x is positive and x is positive, then t has to be also. T has to be greater than 0 too, or equal. So also, x is less than 1 plus x, because we added 1 to x. So if we divide both sides by 1 plus x, then we get that x over 1 plus x is less than 1. This is t, so that means that t is less than 1. So 0 is less than or equal to t is less than 1. Okay, that's the first thing, but we're not there yet. Now we need to show that t to the n is less than or equal to t is less than x. Now, we can see that t to the n is less than or equal to t because we know that t is less than 1. So if you multiply both sides by t, you get t times t is less than t. You multiply both of these by t again, and you get t times t times t is less than t times t, and so on, right? So if you put all these in order, we have that t times t times t, and so on, is less than t times t times t, is less than t times t, is less than t, is less than 1, right? So every power of t, if t is less than 1, then every power of t is going to be even less than that. Therefore, t to the n is less than or equal to t. So now we still have to show that t is less than x, and then we'll have finished. So to show that t is less than x, we do basically the same thing we did above. So we know that 1 is less than 1 plus x because x is positive. So if we add something to 1, it's going to have to be bigger than 1. So then divide through again, and we have 1 divided by 1 plus x is less than 1. Then we multiply both sides by x, and we get x over 1 plus x is less than x. This is just t. Therefore, t is less than x. So we've shown, on the last page we showed that t to the n is less than t. Here we showed that t is less than x. So we've shown that if t equals x over 1 plus x, then t to the n is less than or equal to t is less than x. And what does this mean? The point of this is that the set that we're looking at is the set of all t such that t to the n is less than x. So we just showed that there is one. If we take x over 1 plus x, then the power of that will be less than x. So we've shown that this set at least has something in it. So the next thing we have to show is that it has an upper bound. Okay, so now we're going to show that there's some t that is not in E. So there has to be some t where the t raised to n is going to be bigger than x. We just have to find one of those, and then we'll know that that's the upper bound. So if we look at t is greater than 1 plus x, we know that 1 plus x is greater than x. So t is greater than x also. Oh, we also know that t then is greater than 1. So if that's the case, then if t is greater than 1, then we can do the same thing we did before. Multiply both sides by t, and we have t times t equals t times 1 is greater than, and then t times t times t is greater than t times t, and so on. So then if we put these in order again, we have that t times t times t dot 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 is greater than t times t times t is greater than t times t is greater than t is greater than 1. So here again, if t is greater than 1, then t to any power is going to be even greater than that, meaning it's going to be greater than 1. Okay, so we showed that t to the n is greater than or equal to t, and we showed that t is greater than x. So we have that t to the n is greater than x. So what we've shown is that if t is greater than 1 plus x, then t to the n is also going to be greater than x, which means that this t will not be in E. So what we showed here is that anything bigger than 1 plus x will not be in E. So that means that 1 plus x is an upper bound of E, because anything bigger than that will not be in E. So it's an upper bound of E. Okay, so we showed that E is not empty, and we showed that E has an upper bound. Therefore, we've shown the existence of a least upper bound of E. We're talking about real numbers, which we've defined as being a field that has the least upper bound property, which means that every set that is not empty and has an upper bound has a least upper bound. So the supremum there is a supremum of E, which we'll call Y. So we're just getting started here. This shows how difficult dealing with these objects are, because all we've done so far is show that sup E exists. Now we have to show that, in fact, y raised to the n equals x. So we've just barely started. So to do this, one of the ways that you can show that two things are equal is you show that y to the n cannot be less than x, and y to the n cannot be greater than x. If it's not less than x and it's not greater than x, then it must equal x, okay? That's how we're doing this. In order to do that, we're going to use an identity from algebra. So the identity is that b to the n minus a to the n equals b minus a times b to the n minus 1 plus b to the n minus 2a plus a to the n minus 2b plus a to the n minus 1. Right, so it's just the symmetric. You start with the high exponents of b and no exponent of a, and then you go down to high exponents of a and no exponents of b, all of that times a minus b, and you'll end up with b to the n minus a to the n. Just to make sure we believe that, let's go ahead and do this because the whole proof is based on this fact. So let's just multiply this out and see what we end up with. So first we multiply b times all of this, then we multiply a times all of this. So we have that b times this to the n minus 2a minus a, and then the same thing, b to the n minus 1 plus b to the n minus 2a plus a to the n minus 2b plus a to the n minus 1. Okay, so all we did is we multiplied each one times this. So now if we multiply it through, we have b to the n plus b to the n minus 1a plus, let's say b squared a to the n minus 2 plus b a to the n minus 1 minus b to the n minus 1a minus b to the n minus 2 a squared minus a to the n minus 1 b minus a to the n. So do you see what we just did? Obviously, all of these cancel, right? This term cancels. There's another term here, which we didn't write, cancels with this one. And then this one is one here that we didn't write, cancels with this one. These two cancel, a to the n minus 1b, and we're left with b to the n minus a to the n equals b to the n minus a to the n. Okay. So from this identity, we're going to point out something else. We're going to claim that b to the n minus a to the n is less than b minus a n b to the n minus 1. Oh, only when 0 is less than a is less than b. Because first of all, if they're equal, then that would just be 0. But if a is greater than b, then just switch the a and b. Okay, so we're just saying that it's the bigger one minus the smaller one. That's all we're saying here. Okay, so let's take this onto the next page. Okay, so we're claiming, just write it down again, b to the n minus a minus 8, or b to the n minus a to the n is less than b minus a n to the b, n times b to the n minus 1. Now, remember what our identity said this equals. That b to the n minus a to the n equals b minus a times this thing, okay? So this matches with this. B minus a and then times something else. B minus a times something else. So what we have to show is that this is less than this. So we need to show that b to the n minus 1 plus b to the n minus 2a plus b a to the n minus 2 plus a to the n minus 1 is less than n times b to the n minus 1. So the key here is that a is less than b, because if a equals b, then this term is b minus 1, b to the n minus 1. This term is b to the n minus 2 times b, b to the n minus 1. This is b to the n minus 1, and this is b to the n minus 1. So you have n of these terms. And the reason is because you start with b to the n minus 1, but you're counting down to b to the 0, right? So there's actually 0 1, 2, 3, up to n minus 1. So there's n of these. So if a equals b, then b to the n minus 1 plus b to the n minus 1 plus b to the n minus 1 plus b to the n minus 1 equals b to the n minus 1 plus n times and n times. So what we have to show then is that that's if a equals b. So if a is less than b, then we just have to show that in that case, we have to show that for each term where a is less than b, then in each instance, this is going to be less than the matching term where they were all b. So for instance, one of the terms, this one, b to the n minus 2 a, is going to be less than b to the n minus 2 b, because if you have that a is less than b, if a is less than b and you multiply the same thing by both sides, then you know that this is less than b. That's one of the ordering properties. Okay, so since we've shown that if a is less than b, then every one of these terms is going to be less than the term with if a equaled b, then we've shown that the b to the n minus a to the n is less than this, because this is less than this. So therefore we show that b to the n minus a to the n is less than b minus a n b to the n minus 1 when a is less than b. Okay. Okay, let's start a new page. So with this in hand, we're ready to prove. What we're trying to prove is that y to the n is not less than x and y to the n is not greater than x. And we're going to use this fact to show that.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.